Welcome to another bonus episode of Tearing Rabbit Holes. The idea here is for people who've had roughly 1 year of calculus to get to the essential features of the Standard Model and general relativity, which currently describe all observable experiments, and also form the basis for extensions. So here, I'd like to introduce you to the calculus of variations, as opposed to first-year calculus, in which you might try to find the minimum or the maximum of some function. The idea here is to find a function which extremizes some integral. I want you for the moment to consider a plane with 2 points on it. One can imagine that an infinite number of functions can fit between those 2 points. I can draw a parabola up that goes to those 2 points, a parabola down, or any squiggle that's a function between those 2 points. So there's truly an infinity of functions connecting the points. So I'd like you to consider the question, what is the shortest distance between those 2 points? And you would tell me, it's a line, of course. Well, so what I've done for you is I'm going to try to prove it to you with the calculus of variations. I'm not going to develop this calculus formally, but we're going to use it. This is the Pythagorean distance. If you move a chunk delta x and a chunk delta y, then the distance that you've moved is delta x squared plus delta y squared. And then you take the square root of that, and that's the distance you've moved. If I factor out the delta x squared, I have 1 plus delta y squared over delta x squared, and the delta x squared here. Of course, the delta x squared becomes just delta x. Now, you might recognize that in the limit as delta x tends to 0, this ratio, delta y delta x, just becomes the derivative, dy dx, or y prime. So if I move from some point A to some point B on an integral, and I'm not specifying those at A and B, then the length of this curve is 1 plus 1 plus y prime squared, the square root of that, dx. Or I'm going to call this L as a function of y, y prime, and x. And my goal is to find the function of all the functions between point A and B that minimize the distance. It turns out that the calculus of variations for such a L that depends on on y, its the first derivative, and x, is given by this differential equation called the Euler-Lagrange equation. And you look inside here and you apply this formula to it. The derivative with respect to x of the partial of L, which is partial of y prime, minus the partial of L partial of y, is equal to 0. That's going to lead us to a differential equation. Now, if I look at here, I don't see any dependence on y. So this part here, partial y, partial L, partial y, is 0. It just leaves me this piece. Let's first do this. What is the partial of L with respect to y prime? There's a 1/2 power here, so it's 1/2 minus 1 makes it a negative 1/2, and here we go here and follow with following differentiation inside the radical, y prime to the second power. If I take the derivative of that, it's going to be 2 y prime, and the 2 over here and the half over here cancel out, and I get this. So I see that it's equal to 0. Now, when the derivative of something is equal to 0, it must be that the antiderivative is a constant. So let me multiply out both sides of this equation by dx, square root of 1 plus y prime squared. Well, of course, that leaves me with y prime, which is defined as dy dx, must be a constant. I'll call it m. And when I integrate out this function here, integral of dy is equal to m integral dx, I get y is equal to mx plus b. So I have found the shortest distance between the 2 points is indeed a line. So that's really saying an infinite number of things, but only one of them solves it. And so nature likes to minimize this. Fermat's principle explains why light bends if it goes between, say, water and air. Fermat's principle of least time is that photons will try to follow the path of least time. If you like to play with soap bubbles and wireframes at a children's museum, the surfaces that form, or the bubbles that form, try to attain minimal surfaces that are following this kind of calculus. Now let's take an aside. Let's go to Newton's second law. Momentum in Newton's is defined as the mass times the velocity. Usually we treat the mass as a constant. It's not a rocket throwing out fuel. So we usually think of something as a football with constant mass. Newton's second law is that force is equal to the time rate of change of the momentum. If m is a constant, that leaves us m dv dt, and we recognize that the derivative of velocity with respect to time is the acceleration. Velocity itself is defined differentially as the rate of change of x, the position with respect to time. And so, ultimately, the force is equal to m times the second derivative of x with respect to time, or in physics notation, we like double dots for two derivatives. This is an ordinary differential equation of second order. Now let's go back to a problem called the brachistochrone problem. The problem is, of all the different ways to drop from some height h2 to some height h1, for all the different ways for a roller car to roll down, one of these curves is going to minimize the time. And once again, I can imagine an infinite number of choices of functions, but there will be one function that minimizes the time. And so let's look at that. Let's consider that. How do we combine Newton's law up here to that? So that L has a name. It's called the Lagrangian in physics, and it's equal to the kinetic energy minus the potential energy. And I'm going to use dot notation for derivatives, one dot meaning one derivative. If I follow this prescription here, the kinetic energy is 1/2 mv squared, or 1/2 m x dot squared. And the potential energy is mg times the height above. So in this case, it would be x naught. So in general, the Lagrangian is 1/2 mx dot squared minus mgx. And now expressed in terms of x dots, and t. Previously we had y as a function of x. Now we have x as a function of t. Just a different set of variables, but it's the same calculus. Is going to produce the Euler-Lagrange equations. I'm going to try to follow this prescription. I'm going to look at this Lagrangian, and I'll take the partial derivative of the Lagrangian with respect to x. Well, there's nothing there that depends on x, but there it is. And so dl dx is simply minus mg, and we're done with that piece. Let's look at the partial of L with respect to x dot. Right there's an x dot. If I take the derivative with respect to x dot, it becomes 2 times 1/2, there goes that, mx dot. That is that piece right there. If I take the derivative with respect to time, mx double dot. And lo and behold, if I do mx double dot minus the negative of mg, I get 0. Or if I had solved that, mx double dot is equal to minus mg. The object falls down. Isn't this Newton's law? So the Lagrangian encapsulates the differential equation. In this case, F equals ma, or where a is the constant of acceleration here at the surface of the Earth, negative g. And as we've learned from calculus, we can recognize that it's dx dot dt, and if I separate variables, integrate, I get minus the initial velocity minus gt. If I repeat that process, the position is equal to x naught minus v naught t minus 1/2 gt squared. The key thing is, from a Lagrangian, I recover the differential equation, always Newton's law. And so obviously for more complicated problems that have rotations and vibrations, etc., this is a general method. You just collect the potential energies and the kinetic energies, rotational, vibrational, translational, etc., and the potential energies, and you apply this technique, and you will arrive at a set of usually coupled ordinary differential equations, and you solve it, and you have what happens, the equations of motion. And here's what I mean. Here's a Lagrangian for orbital mechanics. In orbital mechanics about a perfectly spherical planet, which I can replace by a point of mass capital M, and a little planet, a point mass of mass little m. It's 1/2 m radial dot velocity squared plus the r dot, that whole thing squared, and then the gravitational potential energy. And I just noticed that should be r. So let me fix that. And ditto here, same mistake. So that would give us a differential equations in radius and in angular coordinate. However, in this problem, angular momentum is conserved. R squared theta dot is a constant, so I can solve for theta dot in terms of constants. Let's get rid of that and turn it into potential. Okay, if I had a spring, it'd be 1/2 mx dot squared minus 1/2 kx squared. And let me just replace this formulation of kinetic energy with p squared over 2m. So 1/2 mx dot squared is expressed in momentum as p squared over 2m. And here's how the same Lagrangian, using momentum instead of velocity, would appear. Why have I shown you this transformation right here? Because we are now one step away from quantum physics. It was learned that I could replace p by minus IH bar ddx in one dimension. We are dealing here with just all along the x direction. And that would convert, and instead of doing the Lagrangian, we do a transformation in which we deal with the kinetic energy plus the potential energy. It's a canonical transformation. And this now leads us, this plus this transformation leads us to the Schrodinger equation for a quantum spring, the solutions of which would be quantized energy levels. The same method applies. Instead of having conservation of energy and momentum in classical physics, we have the conservation of formal momentum in special relativity expressed by this equation. And then you see p, and you would replace p by the same operator to get this part here, on this side here, derivatives with respect to x, and on this side over here, they found the substitution IH bar ddt. So we'd have a differential equation, second order in time and second order in position, and that would be called the Klein-Gordon equation. If you factor it into two first order differential equations, the coefficients must be quaternions, if you want to look up what that is, and those lead to the Dirac equations, one for the side with the electron and one for the anti-electron or the positron. It captures a lot of physics this way. One would think, let me go back to this, one would think that the Dirac equation, having been derived from a relativistic equation, that it would be invariant under relativistic transformations. It turns out that if you transform a Dirac equation using Lorentz transformations, you don't get back the Dirac equation. You get back some extra terms, and that's not good. Back in classical physics, if we apply Galilean transformation to Newton's laws, we'd expect to get back exactly Newton's laws. And here we're having a Dirac equation being transformed relativistically and not getting us back to the Dirac equation, but rather giving us extra terms. If we carefully iterate this process and to try to correct the Dirac equation on the left, on the right, and iterate until we finally have something that on the left transforms to be exactly the same on the right under Lorentz transformations, those extra terms happen to be Maxwell's equations, which govern photons, the carriers of force in the electromagnetic theory. This idea was propagated to higher symmetry groups for the Standard Model, essentially, for the strong nuclear force and electroic theory, is adding those corrective terms. Just some nerdy aspect of it. These lead to massless gauge bosons, though it's just fine for the photon. It's massless, but not so much for the other theories where the gauge bosons have mass, and you have to develop a theory called symmetry breaking. So let us recall in this here case what the exponential e to the x is when you do a Taylor series expansion of it. It's 1 plus x plus a half x squared plus 1/3 factorial x cubed ad infinitum. Now consider a rotation of the xy plane by angle theta, where theta is a continuous parameter, to some new x prime y prime rotated system. In other words, this is going to be my rotation matrix, and I apply it to a vector x, column vector here of xy to get x prime y prime. Consider that this matrix cosine theta minus sine theta cosine theta can be re-expressed as e to the theta times this matrix. So the exponent of e is theta times that matrix. If I just follow this formula, that would be the identity matrix. That would be the matrix times theta. That would be 1/2 factorial of the matrix squared times theta squared. And continue that process, and then just collect the terms. This is 1 minus a half theta squared, and on. This is minus theta, and theta to the third power over 3 factorial, and on. This is exactly symmetric. That's exactly symmetric. If we continue this, one would recognize that this is the Taylor series for cosine of theta. This is the Taylor series for sine of theta. And so I recover, through this method, I recover that. There's a reason I'm doing this, and we'll come back to it in a second. So in general, in three-dimensional space, I would have a rotation matrix for rotating about the x-plane, the y-plane, the z-plane. These would be the 3 rotation matrices. And expressed in this form, I could just do it. These would be the so-called generators, because e to this power would give you that one, e to the power would give you that one, e to the power would give you that. And I want you to consider in these matrices, a matrix A times a matrix B minus the matrix B times a matrix A is not, in general, 0. This happens in vector calculus, where A cross B is the negative of B cross A. And so the algebra of these matrices is that I have Rx, Ry inside this, called a commutator. I get minus Rz, or let me just replace x, y, and z by 1, 2, 3. And so the ith matrix up here is equal to epsilon I j k, where it's positive if this is a symmetric permutation of the 3 symbols I, j, and k, or negative if it's an odd permutation. This is 1, 2, 3, so that's an even permutation, and it gives me that. And so this is the algebra encapsulated of the commutators of the rotation matrices. How does that connect back to Lagrangians? Forget about these rotation matrices. Consider the definition of angular momentum in classical physics as a cross product. I, unit vector, j unit vector, k unit vector, x, y, z, momentum p, x, momentum in the py direction, momentum in the z direction. And if I just follow that, I will get to this term and that term and that term, or that term. This would be the angular momentum in the x direction, y direction, and z direction, x, y, and z. Oh, but now let me go here in this form and apply that transformation, the classical to quantum transformation, and do it again. These differential operators would have the exact same symmetry as these rotation matrices. Well, of course, they're very connected to each other. Angular momentum and rotation are very connected to each other. Is it the coordinate system that's spinning around the figure skater, or is it the figure skater that's spinning around a frozen coordinate system? That's essentially the difference. Here we think of the coordinate system rotating. Here we think of the object rotating. So the algebra should be identical. So let me explain to you. I've already explained to you that in electromagnetism we have one gauge boson, the photon. Here's one from the Gell-Mann matrix in I believe the strong nuclear force. Here is a matrix, and if you remember your really basic linear algebra, it has eigenvalues and eigenvectors. That is, if you multiply this matrix with that coefficient times that vector, you would get that value times that vector. If you multiply this whole matrix by that, you would get that times that. And if I take this and I multiply it by this, I would get that back with that value. And if I plot it out in the complex numbers, this is what I would get. This is how particles, the gauge bosons, have to appear. This is why we know that there's photons and there's electroweak particles and there's gluons out there. This is for gauge field theories. This is a method that mathematicians and physicists can use to explore the Standard Model, which we slowly piece together by experimental methods, and extensions beyond this, extensions into higher symmetry groups. So at the highest levels, I would say that physics is formulated in differential forms, which is a generalized calculus that applies in arbitrary dimensions in arbitrary manifolds. The sphere is a manifold, the plane's a manifold, the torus is a manifold, but in higher dimensions as well, not just the ones that we can imagine. And in fact, this is a calculus which makes vector calculus look overly complicated once you learn differential forms. There's no Gauss's theorem and the divergence theorem and the Stokes theorem. They're all just operators that generate each other. Lagrangians seem to be the way the universe works, ours. Here is the Lagrangian of the Standard Model. So it's got your electroweak and strong nuclear force. Yes, electroweak in the sense that it's a combined theory. Only when nuclear decays are not involved do we have electromagnetism purely by itself, but really it's electromagnetism is part of the weak nuclear force. And of course there's a general relativity Lagrangian and extensions beyond it. So these are the Lagrangian for the general relativity and the Lagrangian for the Standard Model are what we currently know. We know that it's not correct for many, many reasons. You can Wikipedia problems with physics and see what that comes up with. There's lots of problems with physics right now. Noether's theorem is one of the great sources of understanding where particles arise and many other conservations. Back in classical physics, conservation laws derive from symmetries. If your energy is not changing with respect to time, you say energy is conserved. And so you can shift in time, you can rewind a movie back or forward in time, and you always have energy is the same. And that would be you're invariant under time transformations. If your momentum is constant, then you can move from one chunk of space to another chunk of space, and you always have the same momentum. And that is another symmetry connected with a conservation. Ditto angular momentum. If it's invariant under rotations, then you have conserved quantity called conserved angular momentum. In particle physics, that would be charge, say electron charge, isospin, color, etc. in the Standard Model. And these aren't the only symmetries. There are other symmetries, say topological symmetries. Finally, this kind of formulation of an internal symmetry theory and a geometric theory like general relativity, they both can be codified in fiber bundle theory, which is a combination of geometry, algebra, and topology. And once you have this codification, you can begin to look for gauge field theories beyond the ones that we know. Or you can quickly ignore ones you shouldn't bother with, like the surface of a three-dimensional sphere called S2. It suffers something called the Hairy-Ball theorem, which means that somewhere on a sphere that has a vector field on it, there has to be a point with a vector field's magnitude is 0, and then you can't define differentiation at that point on this manifold. So it's not a good approach to physics. There is S1, the circle, there's S3 and S7, and as far as spheres go, that's it. I don't know about other manifolds, say tori or etc. And there you have it. I mean, this last page here is the big picture, but it's all coming from really basic ideas, symmetries of rotation, symmetries of conservation of energy or momentum or formal momentum in special relativity. The fact you can start at the classical level and write your Lagrangian and then convert it over into a partial differential equations in time position to get quantum physics. If you use general special relativity, you get quantized special relativity. Quantum electrodynamics follows from that. The fact that the universe likes Lagrangian formulation, it minimizes action, is what we say in physics. And that is generalizing Newton's law. So I always think of general relativity and quantum field theories as just nothing more than F equals ma in higher symmetry groups and or geometric manifolds. And there you go. That's how it's connected to the shortest distance between 2 points.